Okay, calculus. 11.2 is about vectors in space. It's basically we're extending the idea of a line with a direction to a 3D area, because calculus 3 has a lot to do with 3 dimensions. In order to do that, we're just going to establish a baseline set of axes. There's two different ways you can look at a 3-dimensional axis. We always let z go up. Something people think x should go left and right because that's more consistent with what it used to do, and y should go towards you. Some people think x should go towards you and y should go left and right. We're going to do x coming towards you, y going left and right, and z going up. Drawing in 3 dimensions is a little bit trickier than drawing in 2 dimensions, but a lot of the things for 2-dimensional spaces apply to 3-dimensional spaces. For example, the distance formula used to be x2 minus x1 squared plus y2 minus y1 squared. It's the square root of that. Now we're just adding in a third variable, but otherwise it's exactly the same. So if you want to find the distance between 2 points that are in 3-dimensional space, you just take the square root of the 3 differences squared. So I'm going to do the first point minus the second one. 2 minus 1 squared plus negative 1 minus 0 squared plus 3 minus 2 squared. That's 1 squared, which is 1. Negative 1 squared is 1. And this is a negative 2. And 5 squared, which is 25. And add those all together, you get distance is the square root of 27. So as you can see, it's not the hardest to implement. So we'll just keep going with other applications in 3-dimensional space. So since the distance formula applies, that means a relationship with circles can also be extended to a relationship with spheres. Since the sphere is a set of all points that are equidistant from a certain center, has a certain radius. And so the formula for a circle used to be, some kind of x squared plus y squared equals r squared, which could move depending on the center. Same thing here, it's now x, y, and z though. And the midpoint formula is just, if you have the midpoint between points, it's just the average value of your x, y, and z's. So if you want to find the standard equation of a sphere that has these 2 endpoints on a diameter, you need to first find the center of that diameter, which is the center of the sphere. So we have the center for x is 5 plus 0 over 2, which is 5 halves. The center for y for negative 2 plus 4 over 2, which is 2 over 2, so that's 1. And z, 3 plus negative 3 over 2 is 0. So we know that our center is 5 halves, 1, 0. Now, if I want to find the equation for the circle itself, I know I've got x minus 5 halves squared plus y minus 1 squared plus z minus 0 squared equals r squared. I just need to take one of the points and plug them in. It doesn't matter which one you plug in. I'm going to plug in the one with the 0. So we'll have 0 minus 5 halves squared plus 4 minus 1 squared plus negative 3 squared equals r squared. I'm not going to put the minus 0 in again. This is negative 5 halves squared plus 3 squared plus negative 3 squared is r squared. So this is 25 fourths plus 9 plus 9. Okay, so this is where we are. This is 25 fourths plus 18, so r squared. This is 72 fourths. So 25 plus 72 is 97 fourths is r squared. So what you do with the r squared is you take it back into the original equation, and you replace the r squared with that number. So the equation for the sphere is x minus 5/2 squared plus y minus 1 squared plus z squared equals that 97/4. If you remember back to your algebra days, you did this with circles. It's just a slight increase in difficulty. Now, if we can have line segments in 3 dimensions, we can also have vectors in 3 dimensions. So you have, for your unit vectors were just I and j. Now we have I, j, and k is the unit vector in the z direction. Other things of vectors that can be extended. 2 vectors can be equivalent if they have the same equivalent components. There's just now 3. Just like the distance formula was extended, the length of a vector is extended. The length is just the square root of the sum of the 3 vectors squared. Adding and subtracting vectors, you still add and subtract the components. Unit vector, you still take the length, you divide each term by the length, and you can still add, subtract, and scalar multiply. So let's see how this works. Find the component form in magnitude of vector v having initial point -2, 3, 1 and terminal point 0, -4, 4. Find the unit vector in that direction. Okay, so to find the vector, we just subtract. So we've got 0 minus -2. It's terminal minus initial always. -4 minus 3. 4 minus 1, just 2, looks like a -7, 3. To find the length, I need to take, so this is the length of, we'll call this u, just because. It's the square root of 2 squared plus -7 squared plus 3 squared. Equals the square root of 4 plus 49 plus 9, which is the square root of 62. So this is the length. Now to find the unit vector, we just take this vector and divide each term by the length. The unit vector is just 2 over the square root of 62, -7 over the square root of 62, 3 over the square root of 62. So again, the concept is not hard to extend into 3 dimensions. Now, a definition of a parallel vectors. 2 vectors are parallel if you can multiply one by a scalar to get the other, because they can go parallel in either direction. So whether you're multiplying by a positive or a negative, it doesn't matter. So let's vector W has initial point 2, -1, 3, and terminal point -4, 7, 5. Determine if it's parallel to either U or V. So W is the vector -4 minus 2, 7 minus -1, 5 minus 3, which is -6, 8, 2. Now, if I can multiply by a scalar to get one of these, I should be able to multiply W, whatever turns W's first term into the U, if they're parallel, it should turn all of them. So -2W equals -12, -16, oh no, sorry, +12, -16, but -4, which is not the same as U, so not parallel to U. Now for V, -2V equals -6, 8, 2, so it is parallel to V, because that's the same as what W is. And we'll do more in the next video.